So I work at CEA-CNRS in France, and my work personally is on solid-state spectroscopy using transient absorption and reflectivity in the XUV. And today I want to show you a bit more on this. I want to give you an overview of the technique, how to perform it, and what people have done using it. So the outline of my talk is going to be an introduction about the principle of the technique, and basically how would you go about setting up an experiment and having a successful experiment. Then I want to show you what has been measured so far, and I want to say that it's just not going to be exhaustive because there's going to be a lot of there has been a lot of experiments done with this technique. So I'm going to talk about different things that exemplify what can be done, and I will talk to you about what I think are the current challenges and the future directions that people are pursuing right now. So going back to the title and then the name of the technique, pretty much. You can separate the name of this technique in two. I like to do it this way. The first part is transient absorption spectroscopy, which is something that's not only done with attosecond pulses. It's something that's done with visible pulses, with picosecond, nanosecond pulses. So it's very general technique. So I want to talk about this first. And then in the second part, I will talk about what's specific about measuring the absorption in the XUV. So the transient absorption in the optical region, it's pretty much what you call perm probe. Usually what people say perm probe, this is what they mean. And it means that you're going to excite a system. Here, I have taken a molecule that you excite from the S0 to S1 state, and you're going to trigger a reaction. You're going to have some more excited states over there, and then maybe you're going to have a product at the end of the reaction. And to follow what happens in this reaction, you send a second pulse, which is called the probe pulse. And depending on the wavelength that you have inside your probe pulse, so here I'm using, let's say, a white light, so there's many wavelengths in a probe pulse, you're going to be able to probe everything, I mean, a lot of things that happen to the molecule that you're exciting. For instance, you will see this blue negative feature, which is because you excited a bunch of molecules that were in the ground state, so now you have less of them. So they're going to absorb less, so this is why you get a negative feature, which is called the ground state bleach. You can also get, here you get some new absorption features that are the excited state absorption. The products that you create are also going to be able to give you another absorption. So this is the red curve here. And maybe you can have also some stimulated emission that you trigger with your probe pulse. And what you do in the end is measure the sum of all of this. And so you measure this black curve here, which is the measurements. And a lot of work for the spectroscopist is to transform, this black curve into all those separate components. And so people use this technique a lot because it has a lot of advantages. First, it's an all optical technique, so you don't have to use any charged particles. So it's rather easy to implement compared to maybe measuring some particles. And most importantly, you can really use any pulses in any wavelengths, and then you can get good time resolution down to a few femtoseconds if you use femtosecond pulses. The second interest of this technique is that you can use different wavelength for your probe. So I've shown you a bunch of electronic properties first. And so if you use indeed photons in the photon energies in the 1 to maybe 6 eV, you're going to probe electronic properties. But then if you use much smaller photon energies, like less than 0.1 eV, you're going to be able to probe some structural information like vibrations or phonon modes. And then by doing this, you can really see a lot of different aspects of the dynamic that you are interested in. But this strength is also a difficulty sometimes because it makes it hard to probe both the electronic and the structural properties together. And sometimes that's precisely what you want to do, especially when they're coupled together and when we work at fast time scales, that happens. And so that's hard to get the two same pictures in the same experiment. And the second difficulty is that, as you saw before, the spectra can get a bit cluttered in the way that everything kind of overlaps on top of each other. And you have a lack of selectivity in your probing step. You kind of probe everything at the same time sometimes, especially when you go to bigger systems. It's kind of hard to get the simple picture of, this product is here, this excited state is here, etc. Which is why it's important to think about going to another spectral range. And I'm going to talk now about the XUV or X-ray spectral range and what changes when we do absorption now in the XUV. So an example of a spectrum here, this is an absorption spectrum that was done in X-ray. So you see here in the 5 keV, so that's pretty far. And this spectrum was taken in barium titanate. That's not important at all. What I wanted just to show you is the basic structure of an X-ray spectrum. And it always looks like this. You have pretty much zero absorption at low photon energy. And then you have a big step here. And then you have some absorption. And this is what we call the absorption edge. And so it always has this, square feature like this. And then on top of this, you get a bit more information. You have sometimes pre-edges features like here. And then you have some fine structure. So this one is called the near edge fine structure. And then you have the extended fine structure over there. And people use these fine structures because they basically arise from rescattering of electrons inside the system. And so you can use these to get information on the structure actually of the system. But what's also interesting is the main interest is the position of this edge and the shape of this edge. And the spectroscopy has been very developed. It's one of the most powerful analytical tool, I would say, both in gas phase and solid state and liquid phase. And this is thanks to synchrotron radiation, because with synchrotron radiations, you can go easily to these high energies and measure this spectra with very, very good quality. Here what I'm showing is a K edge. And so just a brief reminder maybe, or useful notation note. This is what's called the X-ray notation. People that do X-ray absorption always use these numbers, and they compare like this compared to the atomic notation. So the K edge is the 1s core level, and then you get the L edges with the number 2 for the principal numbers, etc. And sometimes when, for instance, you have the M4 and the M5, so they're both 3D electrons, but with different spin orbits, they're split by the spin orbit splitting. And then sometimes they have the same energy, so people refer to that at the M4-5 edge. And all right, and so if I take all of these edges, here I represent kind of a rainbow map of all the core level energies of the first, 93 elements, and I've plotted their binding energies. And so here you see in blue, they're the K levels, and then you get the L, L2, M, N, O, P, etc. So this is as you go, this is the outermost core levels. And so what you see in this map is that all my dots are, rather separate, especially you see this huge energy range, it's very large. And so what you can basically say from this picture is that the X-ray absorption of a spectrum is kind of a fingerprint, because if you measure, some element here, you know which element it is going to be. And so that's important for analytical properties, but it's also important for spectroscopy, because it means that whatever you measure around an edge means it's the local environment of the specific element. And so that's the main strength of the technique, is that we have what we call element specificity. And so we can probe whatever happens around one element of the system, and then we can probe another element at the same time. Another strength is that it's sensitive to coordination chemistry, because since we're using core level for the probe step, the core levels are very localized on one atom. And so you really sense whatever is happening around this atom. And so here I have an example. This is the same spectrum. So this is barium titanate solid. And then here, the middle here is a titanium atom, and you can see it's surrounded by 4 oxygens. And if you now look at this coordination, now you have 6 oxygens, and here you see a very big difference in the pre-edge structure, and that's precisely what happens when you change the coordination, is that you can open or close some transition before the edge. And so this is one of the interests of the technique as well. And the last one I wanted to mention is that you're very sensitive to the oxidation state, because the oxidation state is pretty much the electronic density that you're going to have around the atom. And so this is going to change the energy of the core level by a lot. And so here is an example of sulfur spectra. So this is the sulfur K edge. And here you see a bunch of different molecules that were measured. And if you start from here, you have S2- in terms of oxidation state. And if you go over there, you have S6+. And so you have a shift of energy of 11 eV between the two. So here you can see that you can actually directly measure the oxidation state of the sulfur. And that's really important when you want to analyze the composition of a liquid or a system. And here, actually, this was done because people were looking at petroleum. And so they wanted to have a diagnostic of the oxidation state of the atoms in the petroleum that they were looking at. So this is a lot of work that's been done at synchrotrons. But these methods, as far as I presented them, they have no temporal resolution. And so the basic idea of doing transient absorption in an XUV is pretty much to combine the best of both worlds. So you get the time resolution from the lasers, and you get the nice properties of X-ray absorption. And so this is what I'm going to refer at XUV TA for transient absorption. And basically, you combine the time resolution and the advantages of the X-ray absorption. Now, if you want to do this, I want to show you a bit what type of sources can we use, and how would we go about setting up a beamline to do this kind of things. So what we need is pretty simple. We need a PEM pulse that's in the visible and infrared usually, and then we need a short XUV probe pulse to measure the absorption. And actually, if you look at history, the first experiment of this kind was very a long time ago. It was 30 years ago. And it was done using laser plasma X-ray sources. And so, I mean, it wasn't a very refined experiment. They just, ionized a solid very strongly and then probed the X-ray absorption. But that was the first, I think, XUV TA experiment. Those sources are interesting because they allow you to go up to hard X-rays, but they still have pretty limited tunability because they use emission from atomic lines, and they're still a bit challenging for everyday uses. So so far, the development of this has been pretty slow, although that's starting to change a little bit. Then we have other types of X-ray sources, the synchrotrons and the free electron lasers, so the big facilities. Their interest is that they are very easy to tune in wavelength. You can access pretty much every wavelength that you want. And in the case of free electron lasers, you get pulses that are very intense and with possible short duration, so that's very nice. But then one other limitation actually is that those sources are up to now at least pretty narrow band. And so if you're going to, to scan an absorption spectrum across tens of EV, it means that you have to do a lot of different energy points. And so that's okay if you want to measure just one spectrum. But then if you want to do this as a function of time delay, then now you have a 2D a map of parameters that you have to scan, so time and energy. And so that's very time consuming actually. So far, I think that's been one of the most limiting use of these sources for TA. And also in the case of free electron lasers, you do have still multiple jitter sources that limit the sensitivity of the technique, at least until now. So this brings me to the other type of sources. I'm sure you hadn't seen that coming, which are Attosecond HAG sources. And so the key strength of the sources is that they have an extremely broadband spectrum. So they match extremely well with what we want to do in TA, which is to probe a bunch of different things at the same time. And so have as many wavelengths as we can pretty much in our probe spectrum. And so here I've shown the spectrum of an isolated attosecond pulse. So you see this, in this case, it's extremely continuous. And the idea is that now if you add a sample inside your beam path like this, here I've taken the example of just a nickel chromium sample. So it's 25 nanometer of each element on top of each other. It's nothing too fancy. But here you see that you have kind of a sharp absorption feature that arises here, which is the chromium M23 edge. And here you have two extra peaks that appear here also, and those are the nickel absorption. So, and here they are split by, I think, 2 EV, and so you get the M2 and M3 separately here. And what's going to happen now is that we're going to excite the system. And so if you add a pump to this, you're going to see changes in your absorption spectrum. And here you see some changes that are around the absorption edges. And so that's a generic rule, is that the stronger changes are always around the absorption edges that you look at. And naturally, the strength also that we have is that the pump and probe pulse are locked by intrinsically. And if you look at this picture here, it's not very practical to see the fine changes that we are measuring. So usually we like to plot it differently. And we plot it this way, which means that we compute the change of optical density. So the optical density is this blue curve here. It's pretty much the absorption that we take a log onto the absorption. And then the change in optical density is something the log of the ratio between the spectrum with and without the pump pulse. And so this is the differential measurement. And so the units that we use are optical densities, and usually we measure milli optical densities, so 10 to the minus 3. And so for instance, this orange curve here, I would read this as here we have a maximum level of 18 milli-OD, so because there's a 10 to the minus 3 here. And then we get 18 milli-OD at the chromium edge here, and then we see actually some other features because it's all other oxidation states of chromium that have different energies. And here you also have some signal at the nickel edge. And so this is what we get from one time point, time delay. And then if you want to do the full time delay, this is what you get. And so here we get a transient absorption trace in which we have the energy here and then the pump probe delay here. And then you see the features that arise, and then you can actually probe the dynamics of whatever happens in the nickel layer and then in the chromium layer. So that's a nice illustration of the technique. Now, when we produce our harmonics, what's important? What do we try to optimize? The idea is pretty much to have as much spectral coverage as we can. And so another way to say this is that we want as little holes in our spectrum as possible. And so people have found many different ways of doing this. One example is to first go from single color HAG where you get the odd harmonics. You switch to two color HAG, you get also the even harmonics, so you have more spectral coverage. So that's one way to go about it. You can also tweak the phase matching condition. in his paper here, they were able to show that just by changing the phase matching, you go from the blue spectrum to the red spectrum. So you cover a lot more spectrum. You can also use, of course, isolated Attosecond pulses. I've shown this already, and this is a bit more demanding, but you get a pretty nice and continuous spectrum. And you can also think about going to the mid-infrared driving wavelengths, because then you get a very small spacing between your harmonics, and so you actually cover a lot of spectrum. And when we do this, pretty much the rule is that the probe spectrum can never be too broad, okay, because it doesn't limit your time resolution at all. So you just want it to be as broad as possible, except for one thing is that usually we use, always we use diffraction grading to diffract our XUV and measure the spectrum. And diffraction gratings also have a second order diffraction and third and fourth, etc. And so if the spectrum is too broad, you always get overlap between the first and the second order of a grading. And then that becomes a big issue because you kind of overlap different spectral region, and then you kind of lose the interest of the technique. So in general, we have to use some specific generation gas and also some specific filter to avoid this effect and to pretty much tailor our spectrum to the samples that we want to measure. Now for the experimental implementation, there's been two big schemes about implementing this. This beamline here is the one that was in Garching at MPQ. It was there in 2011. I don't know if it's still the same, but in this paper, this is what they showed. And here, or in this chamber, they make harmonics, and then they propagate the XUV and the driving infrared, actually. And then here they have an interesting device, which is a mirror like this, where you have the inside of the mirror that's on a piezoelectric stage. And then you also have some multi-layer coating to reflect the XUV in a good way. And so by using this piezo here, they can delay the XUV from the IR. And so basically they refocus both of them, the IR and the XUV, on the targets, and then they use it for the pump probe. And so this approach has outstanding timing stability because you pretty much don't have an interferometer. So you have no source of a jitter in your time delay. And it's very energy and space efficient because everything that you send in, you end up using it either to make harmonics or to pump. And it's also very space efficient. The only limit of this approach is that it doesn't allow to change your pump properties too much. For instance, if you want to rotate the polarization or turning it to a circular pulse, it's difficult. Or maybe if you want to change the wavelength, let's say you want to put an OPA or something and then pump in the mid-IR or whatever, it will be very hard to do this with this kind of setup. And which is why the other kind of setup is the more straightforward pump probe, and it's the way. So this is the beamline at UC Berkeley, and here they split the pump and the probe before actually making harmonics. There you do whatever you want to your pump, and then you recombine using a whole mirror with the XUV that you made. And so this is a bit more flexible in terms of both shaping the pump and the probe. But of course, the cost is that the timing jitter is pretty important in this kind of situation. And so it's very less efficient to measure subcycle dynamics, but it's still possible, but a bit more difficult. And recently, actually in Milano, they went for another design where they still do the separate pump and probe arm, but they do it in vacuum. And so you have a lot less fluctuation. And also they have some active delay stabilization. And using this line, they were able to show us the time delay stability of about 48 attoseconds, which is great. So maybe this is the best of both worlds. This gives you flexibility because you can still put whatever you want in your pump here, but you get very good timing resolution. And the last thing I wanted to just mention briefly about the beamlines is that there's two types of detectors that people have used. They're the XUV CCDs. So those are just CCDs that you probably know about, but they were made to be very sensitive in the XUV. And so these sensors have extremely low noise properties. So they're very good at sensing very small signals and with very good dynamic range, but they're extremely sensitive and a bit too much sometimes because whenever you send a bit of infrared on them, you saturate everything pretty much. And so this is why people sometimes use the other type of spectrum, which is you use an MCP that converts your XUV into electrons. MCP is a multi-channel plates. And then you convert the electrons back to photons using a phosphor screen. And then you image this phosphor screen by a normal CCD, a visible CCD. And this is much less sensitive to the IR, and then you have a much bigger area to image your harmonics. But the noise properties of these things are a bit worse. Okay, now that I've talked about the beamlines, I wanted to mention how do we set up a successful experiment? What do we need to figure out when we choose the sample, and then pretty much how to choose the right experiment? So the first question that we need to figure out, I think, is which absorption edge are you going to target? Because this is key to the technique, is that you need to be resonant with an absorption edge. And the first question is, can we measure any of the absorption edges of elements? And the answer is not quite. I want to show here, this is the spectrum of silicon. So here, this is the silicon L23, so those are 2p electrons. And here you have the silicon L1, so there's 2s electrons. And so here you have an edge here, and then you have another one here. And what I want to show here is that not all edges are created equal. You can see already that they're very different. And now let's assume we do a pump probe with this spectrum. And let's assume the pump is going to shift the spectrum by, say, 20 millieV. This is a pretty standard thing that happens when you pump systems. Their spectrum shifts a little bit because you move electrons away or towards the silicon atom. And so this is what you would get for the differential absorption for a 20 millieV shift. And so here you see that the silicon L23, you get a massive shift. It's about 30 signal. You get 30 milliOD, so this is easily measurable. Whereas here you get maybe, I don't know, 1 or 2 milliOD. So this is something that is very hard to measure. And so pretty much this edge, you will never be able to use it to measure a signal. And the rule here is that sharp line shapes in absorption are going to give you strong differential signals. And this is why people love actually the silicon L23 edge. This is actually people used it for the first experiments many times because it's so sharp that it always gives you very easily measurable signals. Now, why are those edges not equal, the L1 and the L23? It's because of the way they decay, actually. Because when we think of the edge, so it means that we absorb an XUV photon. When you send your XUV on your element, you're going to create a hole, it's what's called a core hole. And then this state here that you have is going to decay. It's going to take some time, usually a few femtoseconds, maybe less sometimes, to decay. And then once it decays, then it's gone. And then the lifetime of this process pretty much gives you the spectral width of the line shape, the absorption line shape. And so here, for instance, I've shown the decay. This is the Auger decay of the silicon L23. And so you get some electrons from the valence that fill the 2p hole that you created. And so this is rather slow. So this is why it gives you a sharp signal. Now, if you plot the same thing for the L1 edge, now you create a hole here in the 2s shell. And so it means that here the electron from the 2p region is just right there, and then you can fill the hole. And since the 2p to 2s transition, you have very good radial overlap between the two wave functions. And so this recombination is extremely efficient. It's super fast. It's something that's called a costochromic transition. And so this is an Auger decay in which the hole and the electrons here pertain to the same shell here. And so whenever you have these costochromic transitions, you're going to have a very shallow, featureless absorption edge. So you want to get away from these things. The rule is that you cannot use L1 edges whenever you have 2p electrons, or M1 when you have 3p, or M23 when you have 3d, etc. So you always have to use the outermost shell of a principal number. And so if you, now I can update my map here, and I faded all the edges that we cannot see because they're not sharp enough. And so here you see that a lot of them go away, but we'll see that actually we can still do something with this. And so now if I consider this map, I can wonder why, what kind of sources are going to, allow me to see which edges. And so here, the first thing is to think about the 800 nanometer drivers, so the TISAF. And I mean, you've seen this kind of things for many times during the week. And so if you use long drivers, you're going to get energies maybe up to 100 eV if you use helium to make harmonics. And if you use few cycle pulses, I try to keep the ranges here, the scales about the same. And then you see that you can push the harmonic emission maybe to 160 or 150 eV with helium again. And so you get this map. This is the map that's zoomed in on the TISAF laser. And I can add that here, this range is only accessible if you use short drivers. And I can also add that, if you're like up there, the 150 or 160 eV, it becomes really hard. There's not that many people that have a source with enough photons with TISAF lasers that can actually do experiments using these kind of things. And so what we can see from this is that, well, we have a lot of interesting edges. So for instance, these guys here are the transition metals of the first row. This is the second row, transition metals. So for solid state science, actually, there's a lot to do using these transition metals, and a lot that's been done. But if you're a chemist, then you'll be a bit sad because here, the one things that are missing are those elements here in this one. So it's boron, carbon, nitrogen, oxygen, fluorine, chlorine. So pretty much the specific elements that you want to study, if you were interested in chemistry, you cannot, because they're not there. They're just higher up. And so this has been one of the major drive towards longer wavelengths drivers. And so because of you've seen a lot now, you can access a lot more photon energies. And so here, this is again a spectrum with long driving pulses and a spectrum with few cycle pulses. Oh, I forgot the reference here. This is from Johnson in the Science Advances, something that was measured in the Marangos group. And now you can update this map here for the mid-IR HAG. And here you see that you find your nice atoms that we were looking for. And I can add again that here, this is only possible to attain with short drivers, because you see this nitrogen and oxygen, they're like over there. So they're still a bit challenging to access, but people are getting there for sure. So now what's left to figure out is what kind of sample can you use with this technique. And the key sample properties that you have to think about is the number of absorbers. So this is what you can tune. If you're in the gas phase, you can tune this with the pressure of your system. If you're in a condensed phase, you can tune it with the thickness of your solid. And this is what's going to determine pretty much the level of signal that you can measure, depending on the noise structure of your apparatus. So here, I'm not going to go too much into details, but this is an example. You can go back to it if you want, of how I would go about choosing my thickness. Here I've taken again the silicon sample, and I'm going to assume that my pump is going to change maybe 1% of the absorption of the sample. And then that gives me my signal, that's my differential signal. So the thicker your sample is, the more differential signal you're going to get. And then you have also to consider your noise. And so here I've considered only the photon shot noise and the readout noise in the experiment. And this noise also increases with the thickness, because the more material you have, the less photons you have. And so the more the noise is going to prevail. And so from this, you can calculate the signal over noise ratio. And this is what we get in this example as a function of sample thickness. And here I get an optimal thickness of 125 nanometers. So that's actually pretty thick compared to what we usually use. Usually we go towards 50 or 40 nanometers. And this is because here I've avoided the main source of noise in my calculation, which is the harmonic fluctuations. And so in real life, basically, pretty much you always have to be below 100 nanometers. And so that gives you an idea of what's actually measurable in absorption. All right, so now that I've shown you a bunch of things about how to set up the experiments, I want to show you what people have done with it. So I've tried to show you different types of experiments. If I forgot some of them or didn't show them, it's just because I cannot show everything. And so I want to start with gas phase measurements because it was what people started with. And the first experiment was in this paper, in Nature paper, which was a big collaboration between the Garching group, UC Berkeley, I think Argonne, National Lab was there, and also Lawrence Livermore. It was a big collaboration. And the experiment that was done was on krypton. And so what people did is use a strong field IR to excite krypton. And so they created the krypton ion. And when you do this by strong field ionization, you can create krypton in 2 different states. And you have the whole in the 3p levels, but you can have them in the 3p 1/2 or 3p 3/2. So pretty much you get 2 states that are split by the core, by the spin orbit splitting here. So they have slightly different energy. And so what you get is a superposition of states between these 2 ionic states. And so you're going to have a whole wave function, and it's going to beat as a function of time. And this is precisely what the researchers wanted to measure. And so then they use a probe pulse, which is what was a very short attosecond pulse, to trigger D to P transitions. So you take electrons from the 3D and you put them in the holes that are here, the 3p 1/2 or 3/2. And because your spectrum is wide enough, you can actually probe the 2 states at the same time. You can do the 2 transitions at the same time. And this is what they measured here. This is a map that's become pretty famous now. You see here the absorption spectrum with all the different spin orbit transitions. So between all the different spin orbit components, between the 3D and the 3p. And here I've just highlighted this here. If you do a line out of this, you get oscillations with 6.3 femtoseconds. And this corresponds to the beatings of the whole wave packet here. And so they were able to actually reconstruct this wave packet and kind of observe the way the whole wave packet oscillates as a function of time at the femtosecond timescale. And so that was a first demonstration, and a very nice demonstration of the ability of TA with Attosecond pulses to see electronic wave packets. It's also possible to see vibrational wave packets, and people have worked on this a lot. And here I'm showing an example that was done by Wei et al. And this is in a group of Geneaux. And here they were studying metal iodine. And so something that I should say now is that in the gas phase, since at the beginning, people only had TISAF sources. And so the only edge that you can target that's kind of relevant for small gas phase molecules are iodine and bromine. So you're going to see a lot of experiments that were done at the iodine edge and the bromine edge. And so here, that's precisely what they did. And so they were looking at iodine edge, and they used this molecule and then pumped this molecule. So this triggered strong field ionization again. And so you would get ions from this. But this also excites the neutral molecule. And the strength of this experiment is that you can see both things at the same time. So here you see this feature at about 50 EV, that's negative. And so it's negative, so you can think of the picture I showed in the very beginning. A negative feature is a ground state bleach. So this actually corresponds to the neutral molecule that you now have less of. And here in this ground state bleach feature, you see a bunch of oscillations. And this is because with the pump, you create a vibrational wave packets and you have oscillations inside the neutral. And they were able to measure this with great precision. And actually, they were able to show that you have two mechanisms at play that creates this vibrational excitation. But then on top of this, you also have these positive features here that arrive. And they are at lower energy, and they correspond, again, to the iodine edge. But now, since the electronic environment is different because you removed an electron, they shift in energy by a lot. And so you can see them separately from the neutral dynamics. And so here, if you do the same analysis, so you look at the central energy of the peak, you see a much more complex and with different frequency vibrational dynamics. And that's because, of course, the ion has different vibrational properties as the neutral. And so both this experiment and the one I presented before use strong field excitation. So this allows you to do ionization and things, but it's not precise in a way, you cannot really, you're not very selective in the way you excite the molecule. And so what people have been trying to do a lot more now is to do selective excitation. And I wanted to show this experiment that was done in IBR. So you see those iodine and bromine atom I've talked about that people love. And in this experiment by Yuki Kobayashi, they actually used a pump that was at 530 nanometer, and that was about 8 femtosecond. And when you use this wavelength here in IBR, you can trigger a direct one photon transition from the neutral to this excited state here, which is the B state. And if you do 2 photons, you can actually access this Y state that goes down. But what's really interesting is that when the 2 states, the Y and the B states cross, you have what's called an avoided crossing. And then here you have a possibility of having a diabatic crossing, this is zoomed here, and an adiabatic crossing here. And so this is the kind of things that are really hard to measure because you have very strong coupling between the vibrational motion and the electronic motion. And these things happen pretty fast. And so this is precisely the type of technique that Attosecond chemistry I think is targeted at. And so in this experiment, they measured, I think, this beautiful trace because you see pretty much everything that happens to the molecule at the same time. And so here you start from IBR, the molecule, and then as you pump it, I forgot to say that this B state here is dissociative. So you initiate the dissociation of IBR, and then you get iodine and bromine separately. And so the features that we see here in this trace, you see those black features are negative. So this is, again, the ground state bleach. So this is the IBR features. And you see, again, that you have some oscillations in there. So this is, again, that they create a vibrational wave packets in there, but that's not the main point of the paper. And then you also get the IBR feature, but at the iodine edge. But you also see some positive features here. And those are the very interesting ones. You see those features that corresponds to iodine and iodine star. So this is depending on if you finish on the Y or in the B curve. And the same thing here for BR, so BR or BR star. And what's really cool is that then you can zoom on the first 100 to 50 femtoseconds, and you see that there's a bunch of stuff happening actually in that region. And they were able to show by comparing to theoretical calculation that you have 2 components that arise in this short time dynamics, and that you have both the adiabatic and the diabatic curve crossing at the YB crossing. And so this is like a direct observation, I would say, of this avoiding crossing dynamics. So this is something that's really exciting for physical chemistry. If you want to know more about experiments in halides, there's many of them. I've put 3 here, but there's a way more. And if you go in the references of these things, you will find others. And actually, I see that I've used twice. Sorry about that. All right. And so, so this is what you can do with TISAF lasers. But there's also been development using mid-IR sources that allow you to go higher in photon energy. And notably, they allow you to go to the carbon K edge. And so people talk a lot about this, and they're really excited about this because if you want to look at organic molecules, then if you are able to do experiment at the carbon K edge, you can look at pretty much everything, actually. And so this experiment by Andrew Attar that was published in 2017, it's a very nice illustration of the kind of things that you can study because they targeted a reaction from cyclohexadiene, so that's this ring here, and then this ring actually has a pericyclic reaction. Is the textbook example of a pericyclic reaction in which it opens up and then you end up in the excitation structure. And if you're a chemist, you know a bit about this, and you probably know about the Woodward-Hoffman rules, I think probably more than me. And then those rules tells you that actually to have this ring opening, you need to go through an optical photoexcitation. And so if you use a 266 nanometer photon, then you can actually excite the molecule up to there, and then you have a series of 2 conical intersections. And then if you go through these 2 conical intersections, then you go into the ring opened structure. And that's pretty much exactly what the others studied. And then this is the Transient Absorption map done at the carbon K edge, so at about 285 eV. And here you see this wing on the left side of the spectrum. And the authors were able to show that this wing is actually the 2A state that you populate very transiently before you go to the ring open structure. And so you can see that here you start from the closed structure, and then you see it slowly opening, and then you see this big white feature is the excitation spectrum that's starting to arise. So it's a very nice image of what you can do for molecular chemistry. You should also, if you're interested in this, see this paper that was done at pretty much the same time that studied the sulfur and the carbon K edge in these small molecules here. So this is what I want to show you about molecular dynamics. Now, for solid state, the first experiment was done in 2013, so a little bit later, by Martin Schultz. So it was done in Garching. And they were interested in looking at strong field effects. So what happens when you drive a solid very strongly, and pretty much what happens to the electrons under the strong field excitation. And it was probably natural to start with silica, so SiO2, because it's a dielectric with a huge band gap. It's got a 9 EV band gap between the valence band and the conduction band. And so it means that you can really drive the solid very strongly and only see pretty much strong field effects, because you're never going to be able to excite carriers from the valence to conduction band here. And so the experiment they did was to excite here with this infrared photon and then probe from the silicon L23 edge that lies at about 100 minus 100 eV. And this is what they were able to measure. If you look at the absorption in the conduction band here, you see that you have very nice oscillations at 2 omega frequency, and that they're synchronous with the IR electric field that you use to drive the phenomena. And so the way that these oscillations were interpreted is that the driving field is actually strong enough to distort the bands, both the valence and the conduction bands. And it allows a transient mixing of the valence and conduction bands. And so for a very, very short time, the solid becomes conductive. And so you go from a very, very insulating solid, but when you drive it so strong, you make it conductive for like a fraction of a femtosecond. And so that was a very nice experiment that started a lot of excitement about the subcycle electronic dynamics in solids. Then I can show you different, some more. For instance, now a pretty normal route was to now go towards semiconductors. So go towards solids with a smaller band gap. So for instance, silicon that I've shown here has a 3.2 EV band gap. And so this paper was done a year later by Martin Schultz, and this was at Berkeley. And then the difference between the SiO2 and the silicon is that now the pump can actually excite across the band gap. And so the difference that it makes, if you measure the transient absorption here, is that now you go from zero absorption, let's say, to a non-zero absorption after the pump has gone. Because after the pump, pulse has gone, you still have carriers in the conduction band. So this is why you have a modified absorption. But still, you can see here that you see a bit of a step feature here that's synchronous with the peak of the electric field. And so this shows that you actually also see subcycle electronic dynamics in this semiconductor. And the way these peaks were explained is that, well, this photon here is barely enough actually to excite across the band. So what you need is tunnel ionization. You need kind of a strong field effect to overcome this 3.2 eV. And so this only happens when the IR field is strong enough. So this is why every time the IR field is strong enough, boom, you get a bit of an injection across the band gap. And so here the Kiddish parameter was a bit less than 1. So this was why this was called tunnel ionization. There was another experiment in which they used gallium nitride, which has pretty much the same band gap, but the driving conditions were different. And so they targeted a regime where you have a Kiddish parameter above 1. So here you're in the multi-photon ionization. And here the response is very different. You see that you have 3 omega oscillations when you compare to IR electric field. And so this is a sign that you have actually 3 photon absorption. So now you go from the tunneling excitation to multi-photon ionization. And so, yeah, these oscillations are above a petahertz. So this is one of the first, I think, real observation of a petahertz electronic motion in a solid. If you're interested in the subcycle dynamics, I put here some other seminal experiments there. They were really interesting, but I don't have time to show everything, so you can go have a look at them. All right, so far I've talked about the ultra-fast, attosecond part of the solid-state physics that people do. But actually, a lot of solid-state physics and that people care about happens after that. It happens on the 100 femtosecond to even picosecond timescales. And I wanted to show you that even if you use attosecond pulses, we can still bring interesting insight into this 100 femtosecond to picosecond dynamics. So pretty much attosecond pulses are not only useful for attosecond dynamics. And one topic of importance, I think you will agree, is everything related to energy application. And for instance, a big question in photovoltaic cell is how to extract the most energy from the solar light that you convert into electronic properties. And so if you use a very basic image of a solar cell, if you pump the system with the light from a laser or from the sun, you're going to create excited electrons here and excited holes, and then they're going to cool down as time goes. And they're going to cool down towards the band edge. And at some point, you're going to want to extract the energy that they have to make current. And if you extract it here, you see that this red curve here is the photovoltage that you would get, or here is going to be a bit less, or here is going to be a bit lower. And so pretty much the idea is that you want to slow down a lot the cooling down of the electrons, so that when you're able to extract the energy from the electrons, you have more energy. And so a big question for spectroscopy is how can we measure this cooling down of carriers? And most importantly, how can we separate the cooling down of holes and electrons? Because sometimes they have very different properties. And actually, TA in the XUV solved this issue because, again, we can leverage the very big bandwidths of our probe pulses, and we can probe actually all the valence states and all the conduction states at the same time, but then differently. And so here, this is a very simplified picture, but this is a TA spectrum. And here, let's say the Fermi level is here in the middle. Then everything that you observe here is going to be the whole dynamics because they're happening in the valence dynamics. And what you see here is going to be the conduction bands dynamics. So everything that pertains to the electrons. This is simplified, as I said. If you want to know more about why, you should go read this paper by Michael Zurch. That explains a lot about what you see in this traces. And this trace that I've shown you here is actually from an experiment by the George Verweis group at Illinois. And they measured the dynamics in the lead-alide perovskites. And those perovskites is actually probably the most promising candidates for the future solar cells. So a lot of spectroscopy in this field is targeting as those the solids. And what they were able to show using the XUV transient absorption is actually, it's very interesting. They were able to measure differently, to separate the cooling down of electrons and holes. And here you see the two curves in blue and red. And so they were able to show that you have two regimes. When you have low carrier concentration, they kind of cool down at the same time. And when you excite a bit too much, then the whole dynamics become extremely different than the electrons, and they cool down super fast. And so it's actually very detrimental to the functioning of a solar cell, because all your energy that you had in the whole population is gone now. It decays way too fast for you to extract it. And so this shows that you should avoid this high carrier concentration. And so this is a big problem actually for developing perovskite solar cells. And another kind of slower dynamic is what's called a phase transition, and that's something that's very important for solid state physics, is to classify, different solids as different phases. You have the metals, the insulators, etc. But a very peculiar thing that can happen is the light-induced phase transitions. And it says that when you have a light pulse, you can turn some insulators into a metal. And you can do that almost instantly. That's what people up to now, I've been saying, is that these things are almost instant. But now we get we have the tools to actually see how instant or not instant things are. And so this experiment that I want to show you is from Marike Jager, and this was done in VO2. So this is kind of your prototypical light phase transition, because when you pump it, you go from an insulating ground state to metallic ground state. And what the authors did in this paper is to measure the absorption spectrum of both the insulating and the metallic state. So you can get that by just heating at different temperatures the solid, and then you get this orange and blue curve. And now you do the same thing, but in a time domain, and you measure the XUV absorption. And you can actually measure directly how much time you require to go from the orange curve to the blue curve. And they were able to measure that you do that in 26 femtoseconds. And so this is remarkable, because this is, I think, the fastest measured phase transition so far. And so that's something that's really exciting for future research in this field. And if you go and read this paper, you will see that they actually had to do a lot of work on the sample handling, and specifically in the heat management in the sample, because you want to make sure that at every laser shot, you go from insulating to metal, but then that the system goes back to insulating before the next laser shot. Otherwise, you will measure not the same thing at every laser shot. And so how to evacuate the heat between the different laser shots was a very, very big problem in this experiment. And that brings me to actually one limitation of XUV TA, which is precisely this, is that we use samples that are usually thinner than 100 nanometers. And first of all, that's something that's very difficult to do sometimes for some systems. Like people synthesize very delicate and very intricate solids, and then you call them and you're like, oh, I want one, but I want it to be 10 times smaller than what you can do. And that's always a big problem when you talk to people making samples. So that's one big limitation. And the second one is that since those are so thin, the heat that you deposit with the laser stays there pretty much. You don't have any way of evacuating that heat. And so the thermal load is very, very often problematic. Even when we look at 1 kilohertz, usually we just put too much heat in the system, and we have to find ways to chop down the repetition rate or to wait for it to cool down. And so one solution to this problem that people have found is to now perform experiments in reflectivity geometry. Because if you do things in reflectivity, you can actually use very thick samples, because you just reflect off of the surface. And the only constraint is that it needs to be reasonably flat. So you don't want something that's too rough, because it's going to scatter the XUV. But as long as it's flat, you can measure it. So this opens up a lot of things as to what kind of samples can we study. And then the second good thing is that you have a big substrate below your sample, and so you can evacuate all the heat to that substrate. So that's an interesting development. And actually, when you look at the first reflectivity experiment that's been done, it was a long time ago. It was in 2008. And this experiment that was done at LOA, close to Paris. And they looked at bismuth. And bismuth has a very well-known properties that when you excite it with a laser pulse, you trigger some coherent phonon motion, which is to say some oscillation of the lattice. And they were able to show that the XUV reflectivity is sensitive to that motion. And so that was an important demonstration that we have a lot of information on the electronic properties of solids and molecules, but we also have some structural information, because you're sensitive to the local environment of atoms. And so whenever they move towards each other or away from each other, you can sense that too. Now there's been some more recent papers about reflectivity with, let's say, more modern sources. And if you want to know details, you should read these two. The first one is from UC Berkeley, from Chris Kaplan. And the second one is from the Baker group at Ohio State. And I just wanted to point out that we have revisited this experiment in bismuth very recently. It's just on arXiv. And we measured the same thing. This is the coherent phonons dynamics, but now we measure it with a very broad spectrum compared to what they had back in the day. and we get a more information out of it. So, but I think it was a nice comparison of what changed in the last 13 years. And if you're interested in coherent phonon in general, you should go and read these 3 papers that were published somewhat recently, and they all look at coherent phonon motions in a variety of systems. And except for this, there's not been that many reflectivity experiments, except for these 2 that came out rather recently. And I showed them together because they concern very similar dynamics and very similar systems, actually, because this one that we did in Berkeley was done on magnesium oxide, and this one was done on magnesium fluoride. This one was measured in Milano. And what's peculiar about this trend reflectivity traces is that, well, first you only see signal kind of around time 0. If you go away, you have nothing. And so this means that you have a strong field effect happening. You don't actually inject carriers. But the most intriguing part is that most of the signal, almost all of the signal, comes at negative time delays. And so it means that when you have negative time delays, the XUV is the pump. So the XUV comes first, triggers a core excited state that then is going to decay. And then the near infrared pulse is used to probe the decay of this core excited state. And why did we choose those states in particular is that because there's a resonance in the absorption spectrum that's called a core exciton. So this is a quasi-particle. I don't have too much time to talk about these things, but the 2 experiments targeted the 2 things, whereas this one focused more on, you see small oscillations here that they were able to resolve that we were not able to resolve in our first experiment. And in general, this core excited states dynamic with CEA, they've been studied a lot in the gas phase. And I suggest you go see the lecture by Ashley Friedler after the break, and she's going to talk to you a lot more about this core excited states. Now this brings me to my last part, which is about the current challenges and the kind of future directions that the field is going in, and so you might be interested in pursuing yourself. The current challenges, I think the main challenge right now is the technique sensitivity. Because we cannot detect signals lower than 10 to the minus 3, pretty much, in terms of sort of 1 milliod, if you use that language. And we have to compare this with what people are able to do in the visible and the infrared ranges. And there they measure things on the range of 10 to the minus 5 or minus 6. You know, they're going towards measuring pretty much the absorption of a single molecule. And they're building experiments that are able to resolve these kind of things. And so in comparison, we are really bad at what we do. You know, this is like 3 orders of magnitude. And as a consequence, we have to create strong signals because otherwise we cannot measure them. So to do this, we pump samples very hard. And so this is a big problem because we get close to the MET thresholds and we are not very delicate in the way that, you know, we cannot nicely tune the intensity and see what happens because we don't have this much sensitivity at all. The second big problem is that we cannot study very dilute samples because we just need a lot of absorbers to give us strong differential signals. Otherwise, if you just have, you know, a few molecules, then we're never going to be able to see what they actually do. And so this prevents the use of, you know, the study of solvated species that are going to be dilute in some liquid, for instance, or the study of monolayer solids, because when you have just a monolayer of a solid, it just doesn't absorb enough for us to see. And this limit of sensitivity, I think, comes mainly from, you know, the stability of harmonic sources. I know you know, it's getting better and better every time, and people keep improving these things, especially with new lasers and so on, but it's still pretty poor compared to just a laser. And the second point is that we have always pretty slow detectors. For instance, the XUV CCDs that I've mentioned, they have readout times of about 20 milliseconds at the very fastest that it is able to do right now. And so this prevents you from doing any, you know, heterodyne detection or locked-in detection that people do in the visible to improve the sensibility. So I think we must keep improving these. But in the meantime, people have came up with some solutions. Some solutions are, let's say, hardware solution because it's ideas of using references. So if you have 2 XUV beam, one is absorbed by the sample and the one is not, then you can actually normalize all the harmonic fluctuations. And so these 2 papers do precisely that. And then another class of solution, I could say it's software solutions. And those are post-treatment noise that use the correlation that you have inside your harmonic spectrum to reduce the noise that you have in your experiment. And I suggest you go see this afternoon the virtual lab by Nicolas Di Palo, and he's going to show you some of these techniques. Now for future directions, so there's many of them, but I've just picked a few. And one of the most exciting one is what's happening right now in the way of chemical dynamics of this carbon, nitrogen, and oxygen KH. Soon, it will be possible to combine isolated Attosecond poles that are covering 300 to 600 eV, and people are already starting to use these pulses for real experiments. For instance, you have this very recent paper that was done in Zurich, where they managed to measure a sub-7 femtosecond electronic relaxation at the carbon K edge. So this is a very impressive feat. You have also this experiment that was done in Japan at the nitrogen K edge, so at 400 eV, and they were able to measure electronic wave packet. They were also able to see some vibrational and rotational excitation in their spectra. So this is also really exciting work. And soon we will be able to combine all these nice things with the short UV pulses that you heard about during the week. So by many techniques now, it's possible to create pulses that are a few femtoseconds or at least 5 or 6 femtoseconds. And by combining these two, it's sure that it won't get like to a universal method, because with this you can probe pretty much any organic molecule, and you have selective excitation because you have short UV pulses, and you have selective probing because then you can probe the carbon, nitrogen, and oxygen separately, and so you can see what happens to different parts of a molecules, for instance. And of course, you have great femtosecond resolution. To this, I should add that there's also very recent work on doing experiments in the liquid phase that's extremely challenging, and those experiments are like first step towards achieving these kind of things. But I'm sure in the first few years, everything will be combined and do nice photochemistry. Another prospect that's really interesting is to do experiments with those visible attosecond pulses that, for instance, John Travers presented on Monday. And there's two techniques, I think it's fair to say, that allow to create those field transients that last less than a femtosecond in the optical domain. And so using these things as a pump, then pretty soon it will be possible to create attosecond pump and attosecond probe experiments. And I say pretty soon, but it's actually done already. People have done in Garching, and so that was done by Moulet and co-worker, and that was measured in SiO2, so some system as I mentioned, but here they looked at core excitons, so in this big dielectric. And here you see the transient absorption trace that was done here, and you have a signal that lasts only 2.5 femtoseconds, because the pump is so short, the probe is so short that they're able to actually resolve the decay of the excitonic state directly without doing any assumption. And I think that that's really beautiful and very exciting for the future. And finally, something that I haven't talked about at all is anything pertaining to spin. And so I've showed you that CEA, it's powerful to see electronic and structural dynamics, but now it's becoming possible to probe spin dynamics as well. And this is becoming possible because now we are able to produce circularly polarized, isolated attosecond pulses. We've had a talk on this yesterday. And now that we can do this, we can actually combine the absorption with measurements of secular dichroism, and that's particularly powerful in magnetic samples, to go look at very fast spin dynamics. And the last example I wanted to show was this paper by from Zegrist et al. Was done in TU Grast in a group of Martin Schulz. And there they were able to produce the circular XUV pulses to measure the XMCD of a multi-layer system. And using this, they were able to measure the spin dynamics at the few femtosecond timescales. And they were able to see that when you create a multi-layer structure like this, you actually start to demagnetize the system already at the first femtosecond. And so that's something that's surprising, very surprising for studies in magnetism. And I think that's like the first important step towards the study of coherent magnetism. That's something that we know pretty much nothing about. With this, I want to thank you for your attention. I'll leave you with some resources on general TA in the visible and core level spectroscopy, and also some reviews about Attosecond, Transient Absorption spectroscopy, that you can go and read if you're interested in learning more about this. I want to give many thanks to everybody in the Steve Leone's and Dan Newmark group at Berkeley. I was a postdoc there until not that long ago, and that's where I learned most of what I presented today. And if you have questions, or if you are interested in job or collaboration opportunities, just feel free to reach out at this email address. And thank you.